What's going on, my AP Human Geography e-learning students? It's Mr. Majewski here. I am producing this video lecture for week 2 of the year. Now that's obviously Unit 1 and the first week that we have actually covered human geography material. So this information is included in the textbook reading, key issues 1-1 and 1-2. However, it's important enough that we should spend a little bit of time reinforcing it. So the main topic is place and location, but we have some odds and ends of some other things as well that are important that you know. So to begin with, we should probably start with map scale. So scale is simple, right? It's the relationship between what's displayed on the map, right, and that piece of land on Earth's surface. And it's important to know how much of Earth's surface is being displayed on the map that we are looking at. Well, you can display that in a number of different ways. So if you look on a map, obviously there's going to be a key, right? The key is basically a box usually that has information about the map, and one of the things that's going to be included is the scale. There are 3 primary ways to measure or to show map scale, and it's really up to the cartographer. It's up to the map maker to make that decision. So the first is called ratio or fraction, and that's really simple, right? The first number before the colon indicates the size that's being displayed on the map, and then after the colon indicates the equivalent size on Earth's surface. So if there's no specific difference in the unit of measure, you can assume what's being displayed on the map is the exact same unit of measure that's being displayed on Earth's surface. So for instance, 1 to 1,000 would mean that if it's 1 inch on the map, it's 1,000 inches on Earth's surface. This can also be displayed as 1 over 1,000, like a fraction. Same thing, alrighty, it's just up to the map maker as to what they prefer. Now obviously, usually what we see is like 1 inch or 1 centimeter equals, 1,000 feet or 1,000 miles. So usually you'll see a difference in the unit of measure from the first to the second number. But if not, you just know that they're the same measure, whatever it is that you are figuring out. A couple of other quick ways to display scale. Written, this is pretty obvious. You just write it out. 1 inch equals 1,000 inches, right? Or what's very common is a graphic scale. They'll give you a line in the corner of the map in the key, and they'll say that line equals a certain distance on Earth's surface. All of them are saying the exact same thing. All right, it's just a different way to depict that information. Now, the key concept with scale, and this might seem counterintuitive, alrighty, so stop and bear with me. Larger scale maps zoom in. Smaller scale maps zoom out. Alright, so in a lot of ways, when we're talking about scale, we're really talking about detail, right? How much detail is being depicted on the map. On a larger scale map, we're going to get a smaller piece of Earth's surface, but we're going to be able to see it in much more detail. Alright? And obviously, depending on what it is that you're trying to display, that can be really important. That can be exactly what you're looking for. A smaller scale map means you zoom further out, so you see more of Earth's surface, but you don't see it obviously in as much detail because more of it is being displayed. So again, large scale maps, closer. Smaller scale maps, further out. So if I said, hey, we want to analyze the patterns of movement at your school, right? Whatever school that is. Well, we don't want a small scale map that shows us the world or that shows us even California or, to be honest with you, even Anaheim. We want a larger scale map that we can zoom right in on your particular school, right? And check out the movement and the flow of people throughout the day. All right, so please keep that in mind. They love to ask questions about that on the AP exam. Because sometimes it's counterintuitive to some kids. And if you look over at the corner here on this slide, you can see what we mean. This is actually at the top, the smallest scale, right? And then as you go forward, right, you get to see it closer detail, right? So that's larger, and then that's the largest scale right here, where you're zoomed in literally on the neighborhood and can see buildings, right? We can see major landmarks, as opposed to this smaller scale map where we just see the entire state of Washington, which is helpful, but doesn't really tell us necessarily what we need. So that is that. Let's get to projection. We know a projection is a map. We know that every map has error. Every map has distortion. There is no map that is 100% correct. A three-dimensional object on a two-dimensional surface without there being some sort of error, pull, push, distortion. All right? Now remember, there are 4 types of distortion. Shape. Sometimes maps get shapes wrong, right? So a map might have the shape of a particular place wrong, for instance, South America, in order to get the other 3 types right, or in order to minimize the type of error in the other 3 categories. Also distance, right? Distance can be off. A location can be further or closer on Earth's surface than it appears on the map. And again, this would be because you are trying to get the other types of distortion as small as possible, and so you're willing to allow there to be some distortion with distance. Size or area can be off, right? So places can appear smaller or larger than they actually are. And that's the big problem if you remember with the Mercator map. Mercator map focuses on direction, getting those right, but at the expense of size, right? Land, area, and direction, yeah. Sometimes locations can, in fact, point places, right, point land masses in the wrong direction. They can be pointed, or they can be facing a different direction than they actually are on Earth's surface, right? So anyways, all of those are types of distortion, and you do need to know the 4 major types of distortion because they love to ask questions about them. All right, so if you're analyzing a map, always keep in mind that it is not 100% correct. And so let's watch a quick video that really helps to explain distortion in a really easily understandable way. So it's about a 6-minute video.
If I want to turn this globe into a flat map, I'm going to have to cut it open. In order to get this globe to look anything close to a rectangle lying flat, I've had to cut it in several places. I've had to stretch it so that the countries are starting to look all wonky. And even still, it's almost impossible to get it to lay flat. And that right there is the eternal dilemma of map makers. The surface of a sphere cannot be represented as a plane without some form of distortion. That was mathematically proved by this guy a long time ago. Since around the 1500s, mathematicians have set about creating algorithms that would translate the globe into something flat. And to do this, they use a process called projection. Popular rectangular maps use a cylindrical projection. Imagine putting a theoretical cylinder over the globe and projecting each of the points of the sphere onto the cylinder's surface. Unroll the cylinder and you have a flat rectangular map. But you could also project the globe onto other objects, and the math used by map makers to project the globe will affect the way the map looks once it's all flattened out. And here's the big problem. Every one of these projections comes with trade-offs in shape, distance, direction, and land area. Certain map projections can either be misleading or very helpful depending on what you're using them for. Here's an example. This map is called the Mercator Projection. If you're American, you probably studied this map in school. It's also the projection that Google Maps uses. The Mercator projection is popular for a couple of reasons. First, it generally preserves the shape of countries. Brazil on the globe has the same shape as Brazil on the Mercator projection. But the original purpose of the Mercator projection was navigation. It preserves direction, which is a big deal if you're trying to navigate the ocean with only a compass. It was designed so that a line drawn between 2 points on the map would provide the exact angle to follow on a compass to travel between those 2 points. If we go back to the globe, you can see that this line is not the shortest route, but at least it provides a simple, reliable way to navigate across the ocean. Gerardus Mercator, who created the projection in the 16th century, was able to preserve direction by varying the distance between the latitude lines, and also making them straight, creating a grid of right angles. But that created some other problems. Where the Mercator fails is its representation of size. Look at the size of Africa as compared to Greenland. On the Mercator map, they look about the same size. But if you look at a globe for Greenland's true size, you'll see that it's way smaller than Africa. By a factor of 14, in fact. If we put a bunch of dots onto the globe that are all the same size, and then project that onto the Mercator map, we will end up with this. The circles retain their round shape, but are enlarged as they get closer to the poles. One modern critique of this is that the distortion perpetuates imperialist attitude of European domination over the southern hemisphere.
The Mercator Projection has fostered European imperialist attitudes for centuries and created an ethnic bias against the Third World. Really?
So if you want to see a map that more accurately displays land area, you can use the Gall-Peters projection. This is called an equal area map. Look at Greenland and Africa now. The size comparison is accurate, much better than the Mercator. But it's obvious now that the country shapes are totally distorted. Here are those dots again so that we can see how the projection preserves area while totally distorting shape. Something happened in the late 60s that would change the whole purpose of mapping and the way that we think about projections. Satellites orbiting our planet started sending location and navigation data to little receiver units all around the world.
Today, orbiting satellites of the Navy Navigation Satellite System provide round-the-clock, ultra-precise position fixes from space to units everywhere in any kind of weather.
This global positioning system wiped out the need for paper maps as a means of navigating both the sea and the sky. Map projection choices became less about navigational imperatives and more about aesthetic, design, and presentation. The Mercator projection, that once vital tool of pre-GPS navigation, was shunned by cartographers who now saw it as misleading. But even still, most web mapping tools like Google Maps use the Mercator. This is because the Mercator's ability to preserve shape and angles makes close-up views of cities more accurate. A 90-degree left turn on the map is a 90-degree left turn on the street that you're driving down. The distortion is minimal when you're close up. But on a world map scale, cartographers rarely use the Mercator. Most modern cartographers have settled on a variety of non-rectangular projections that split the difference between distorting either size or shape. In 1998, the National Geographic Society adopted the Winkle triple projection because of its pleasant balance between size and shape accuracy. But the fact remains that there's no right projection. Cartographers and mathematicians have created a huge library of available projections, each with a new perspective on the planet, and each useful for a different task. The best way to see the Earth is to look at a globe. But as long as we use flat maps, we'll have to deal with the trade-offs of projections. And just remember, there's no right answer.
Okay, good stuff. Really nice video there to help us better understand this concept. Yeah, so you gotta trade it off, right? You gotta decide which one's most important to you. Okay, excellent. So now that we understand kind of map and map scale and map projection and distortion, which are important concepts in Unit 1, we need to go to the next. And one of the basics of human geography is the concept of place, all right? Place, every place on Earth's surface is unique. We know that, right? Just like every one of us is unique. Places are the same way. Geographers have to be able to describe the location of a place, right? And a place is just a point on Earth's surface. They have to be able to describe that location, whether it's a place or a series of places, which we call a region, and in order to determine really what features it has, right? What physical features and what popular features, meaning features of the people that live there. There are four primary ways that we as geographers identify the location of a place, right? We've got toponym, which is another fancy word for the name of the place. We have site, we have situation, and we have mathematical location. So those are our four primary ways that we identify the location of a place. Now the first three, toponym, site, and situation, they don't tell you exactly where that place is, right? They can't pinpoint its exact location, right? If I say, hey, I'm in Anaheim, well, you know where I am, but you don't know exactly where I am in Anaheim, right? Similarly, if I describe the site and situation, that's going to give you an idea of where I am, but it's not going to be able to pinpoint it. Whereas mathematical location, that last primary way, is the way that we're able to mathematically or absolutely pinpoint our location using latitude, longitude. So those first three types are relative location. The last is called mathematical or absolute. So toponym, very simple. It's the name of a place. Many locations are inhabited by people, so the easiest way of identifying it is by its name. And there's a lot of different types of toponym, right? Toponym can be descriptive, like the Rocky Mountains, right? It can be named after an event, right, like Battle Creek. It can be named after a person, right, like Pittsburgh. It can be, you know, a commendatory name, right, like Pleasant Valley, right? Or it can come from, you know, the local population in an area as well. For instance, many places are named after tribes, Native American tribes in the United States. So toponym is our first major type. The second major type way that we identify the location of a place is site. Site is simply describing a place based on its physical character or features, right? So if you're talking about a place by describing its climate, its water, or its soil and vegetation, maybe its elevation, right? Any specific physical feature, right? Not man-made. We're talking about natural physical features here, then you are describing the site. So site factors have helped people to choose where to settle, right? Valleys, hills, coastlines, deserts, right? For different purposes, people have settled in different areas. And when we describe a place, oftentimes one of the first ways we do it is describing its physical characteristics, describing its site. So Anaheim, a good example of the site for Anaheim. Anaheim's located on a Pacific coastal plain with a warm, mild Mediterranean climate. The fertile soil and the flat land are supported by the Santa Ana River and other nearby freshwater sources, and so citrus farming developed as a result. So do you see how we've described it based on its physical characteristics and helped to explain why people chose to settle there because of the physical aspects of the place? All right, so that's site. Situation is describing the location of a place compared or relative to other places nearby it. It's really useful for finding the significance of an unknown location. So for instance, if you don't know where a place is, but you know other features that are around it, then you are describing the situation. And you know, we do this a lot. If you're on campus and you're trying to tell your friend where you're at, right, and they don't specifically know, you're probably going to describe it based on other features on campus that they do know in order for them to be able to find you. So Anaheim is situated in western Orange County, just southwest of Los Angeles and 100 miles north of San Diego. I should also mention Anaheim's really in northern Orange County more than western, but hey, whatever. It's about 20 miles from the Pacific Ocean and it sits on the Santa Ana River. Because it's situated alongside so many freeways, it has grown enormously in population. So here, are we really describing the physical features? No, right? We're describing where it is compared to other locations around it. All right, so that's situation. Situation oftentimes helps to explain maybe man-made reasons why a place has come to be formed. All right. Those are all relative location, right? They kind of tell us in a relative way where a place is at, but they don't tell us exactly. And so if we need to know exactly where a place is, we have to use mathematical location, right? Latitude and longitude. So I'm not going to spend much time on this because there's a cool little site we're going to go to and read together afterwards as the last part of this video. But mathematical location is a grid system has been developed to mathematically determine any point on the globe. You are probably familiar with the terms latitude and longitude. Now those are invisible lines that have been constructed by man to make it better, more easy for us to travel and to know exactly where we are when we are moving around the world. So what mathematicians have done and geographers have done is they've drawn imaginary lines that connect at the North and South Pole. All right, and they all go around Earth evenly, right? And those are known as meridians, right? And so sometimes also known as lines of longitude, right? And here they are, right? They all connect at the North and the South Pole. Now, the guys that came up with it were English geographers, and so they decided the line that went through where they were is going to be called the prime meridian. They developed it in a place called Greenwich, England, and so 0 degrees longitude is also known as Greenwich Mean Time. All right? Every other meridian on the globe is assigned a number between 1 and 179 degrees based on where it's located, either east or west of the prime meridian. So for instance, Anaheim is 117 degrees west of the prime meridian, so we are 117 degrees west longitude. All right. Meanwhile, if you go to the exact same spot on the opposite side of Earth from Anaheim, you are located in Jinan, China, which is 117 degrees east. So again, 180 degrees west lines of longitude extend, right, to the other side of Earth, and then 179 degrees east, right? And the line on the opposite side of the world from the prime meridian is known as the international date line. That would be the 180 degree line for both east and west where they intersect. Alrighty? The international date line, by the way, is in the middle of the Pacific Ocean, and it's technically where every day begins. Alright? They start each day first, and then slowly over time, right, that day then begins at every other meridian around Earth's surface. Alright? So anyways, that's longitude. At the same time, we have latitude. Now, latitude are sometimes called parallels, and they are actually lines, they're actually circles that are drawn around the globe from east to west. And the one that is directly in the center of Earth, right, is 0 degrees latitude. That's called the equator. And each line of latitude, right, extends either north of that or south of that. Now, because of the way that these lines are set up, the lines of latitude only extend up to the poles, north and south, right? And so the highest possible latitude that you can be is either 90 degrees north or 90 degrees south latitude. So Anaheim has a latitude of 34 degrees north, which means we're 34 degrees north of the equator. So once again, if you are figuring out our location, our mathematical, we are at 34 degrees north and 117 degrees west. All right? In case you're wondering, 34 degrees south, right? So the exact opposite latitude from us is Cape Town, South Africa. Alrighty, so all you simply have to do to figure out your mathematical location is you got to pinpoint your latitude and your longitude. Every point can be located mathematically on the globe. If you want to even get down to more specific, right, every single line of latitude can be broken down even further. So a degree for latitude or longitude can be broken up into smaller units of measurements called minutes as well. They don't talk about time, right? That's just another unit of distance measurement that was created to break up degrees into smaller units. So again, it's very, very, very easy to mathematically determine your location so long as you understand the concepts of latitude and longitude. By the way, where do we see latitude and longitude on a daily basis in our everyday lives? Well, with time zones, right? Every time zone around the world roughly corresponds to about 15 degrees of longitude. So for every 15 degrees of longitude you move, that's going to be a new time zone that you have entered. All right, so it's part of the reason why we have the time zones and the system of time that we have because of latitude and longitude that were created. Climate is based off of latitude, right? So depending on how far you are from the equator, right, which remember is 0 degrees, and there it is, then you're going to be in slightly different climate zones. So the areas around 0, right, around the equator are called tropical zones, all right? They are very humid, a lot of rainfall, a lot of rainforests. Then as you go either north or south of the equator, you start to enter into what are called semi-arid or desert locations. All right, so for instance, 10 and 20 degrees north here, right? You notice dry, arid areas over much of it. If you go down to the same location 20 degrees south of the equator, you see a lot of dry, arid areas there as well, right? As you get into the 30 latitudes, 30s and 40s, now we move into what are called warm mid-latitude climates. These are usually considered more temperate, all right? This is where a lot of folks around the world actually are clustered. And that would include us. So you start to get, you know, subtropical, Mediterranean, right? You're starting to get more just temperate climates, usually better for agriculture. If you come down to between 30 and 40 in the south, you'll see a lot of the same types of climates there. And then further than that, as we get above 40, right, we get into 40 and 50, we're starting to get into the colder latitudes, right? You know, where you're going to see a lot of snowfall in the winter. And then by the time you really get into the high 40s or 50s, we're into the polar or Arctic latitudes. So depending on what latitude you're living in, right, that's going to truly affect the climate that you are used to, that you experience, okay? We have, in many ways, in Southern California, what is considered to be an ideal climate for any lifestyle and for agriculture as well. All right, so those are ways that you really see latitude and longitude in your everyday lives. It's affecting you in ways that you may not otherwise be aware. All right, so folks, one last thing I would like to go to is a link that is right underneath this slide, I should say this Google slide, on our Schoology page. This is Understanding Latitude and Longitude, and I want to finish with this because I want to make sure you folks really understand this, right? So again, I'm going to kind of summarize. I'm not going to read the whole thing. I'm going to leave it for you to read. But really, every location has a global address, is what we like to say. This global address is determined by latitude, longitude. So again, you've got the equator here, right? That's 0 degrees latitude. And then we have lines of latitude that extend upwards. Now, we don't display all of them. Otherwise, Earth would just be like, 90 lines up to there, 90 lines down there. It'd be hard to differentiate or make them out. So we usually display them every 10 or 15 degrees, right? This one is displayed every 15 degrees. So that's 15 degrees north all there, right? There's 30 degrees north. There's 60 degrees north. There's 90 degrees north, right? Same, southern, right? 15, 30, 45, 15, 30, 45, 60, 90 down at the bottom there, right? We can do the same thing with longitude, right? There's the prime meridian there. You see how it goes right through England right there. And then where you are, well, are you west of that prime meridian? Are you east of that prime meridian? And how far are you west or east? You put them together. When you list it, you list latitude first, right? So for us, once again, we would be about 34 degrees north, and we would be about 117 degrees west. That would be our mathematical location in Anaheim. Again, you can pinpoint it further if you'd like, right? You can break it down even into minutes, right? Which allows you to break up each of those degrees into 60 smaller units of measure as well. Hey, I have a couple of really great videos to watch related to this. One of them is really just a nice, awesome explanation of it. It does a great job of explaining it. The other actually helps you to figure it, to determine it, to practice finding locations on Earth's surface. There's a quiz on this, right? Or I should say there's a practice activity on this. So you definitely want to watch those videos, right, before you do the practice activity. Even though they're technically optional, I really highly recommend that you watch them. Folks, I think that's it for place and location. If you have any questions on this, please comment, right, directly to me or send me an email. But again, make sure you know the 4 ways that we determine the location of a place. Make sure you understand the idea of distortion, and make sure you understand the idea of scale as well. Without further ado, it's Mr. Majewski. I'm signing off here. Hopefully you're really starting to get into the materials and the topic for this unit. Have a great, great rest of your week, folks. Mr. Majewski signing off.